They told us we couldn't possibly succeed.
At the end of the 1960s, NASA starts work on its most daring planetary mission, placing 2 spacecraft on Mars to search for life.
To say that that was an easy process would be a huge mistake.
Project Viking will challenge engineers to the extreme. Not to build big, but to build small.
You're talking about a biological laboratory, and you're shrinking it down to a box 1 foot on each side.
Well, who are we kidding? It would never work.
I'd say it almost brought us to our knees.
To succeed requires a spacecraft that must work by itself, millions of kilometers from Earth.
And if any of that goes wrong, it's game over.
As mankind plans a return to the Red Planet, this is the story of the unsung heroes challenged to make the first successful landing on Mars. July the 20th, 1976. The Jet Propulsion Laboratory, California. Project manager Jim Martin and his team of engineers are on the verge of making history by safely landing the Viking spacecraft on Mars.
638, okay.
Over 300 kilometers above the surface, Viking 1 begins its critical descent.
Flag deploy. Confirm roll over.
And this must have been one of the most anxious experiences one can imagine.
59,000 feet. Could be close to mortar fire.
Every engineering device must work perfectly.
Your heat shield has to come off at the right moment. Your parachute has to deploy at the right moment.
Lander confirmed parachute deploy. 3-1, TM2.
And then that last descent coming down to the surface.
Parachute separation. 177 feet per second.
We were at a critical stage.
Suddenly, Jim Martin's phone rings.
Jim got a call from President Ford.
The president's on the line, and he wants an update.
Good roll, attitude hold.
He told him he couldn't talk to him now, he was too busy. And he hung up on him.
After 7 years of planning, all Jim Martin and his team can do
73 feet per second. Come on.
is hope Viking makes it safely to the surface. The story of Project Viking begins in the 1960s. With the success of its first manned moon landing, NASA starts planning an ambitious planetary mission. The destination, Mars. Although smaller and further from the Sun than the Earth, our neighboring planet has some startling similarities.
It has seasons like the Earth. Its day is roughly 24 hours long like the Earth. It even has ice caps like the Earth.
The planet's likeness to ours is so strong, NASA designs Project Viking with one goal in mind.
One of the overarching questions in all of science is there life outside the Earth? And that's the unique thing about Viking. Viking was a science-driven mission.
At over 300 million kilometers away, the search for life on Mars will test engineers to the extreme.
To think we could do this was an absurd assumption.
We knew nothing about Mars at the scale of a lander, or nothing about what it was really like on the surface.
We didn't know whether Viking would sink in the dust. We didn't know whether it would hit a mountain.
During the 1960s, one reason Mars remains enigmatic is the challenge in reaching it. The Soviets and Americans launched numerous missions, many ending in disaster.
Mars is much tougher because it's so much farther away. You have to be incredibly precise. The targeting, the navigation through millions of miles of space.
For Gus Gustafaro, Viking's deputy project manager, it's a journey full of unknowns.
Therefore, we were going to write a spec that had a lot of TBDs in it. And we're going to have to get these TBDs answered. And you know what TBD is? It's to be determined.
The best way to search for life on Mars is to land there. How to do that safely is one of the engineers' biggest challenges. They must choose one of two options.
Option A was to send a lander directly to the planet and have it land without going into orbit first.
It's called direct entry. On arriving at Mars, a flyby module releases the lander, which descends straight to a predetermined location.
You don't go into orbit first, you just come screaming in and you slow down, you get to the surface. So with direct entry, you're gambling big time. You're just coming in and hoping for the best.
The alternative, option B, involves an orbiter that carries the lander. On arrival, they both go into orbit around Mars. The lander then separates and descends to the surface. It's called the out-of-orbit mode. For Viking design manager Norm Krabel, option B has one big advantage.
If you do out of orbit, you establish an orbit and take advantage of that and do some reconnaissance and decide, can I go in where I wanted to, or do I have to go someplace else?
There's no better redundancy than reconnaissance before the attack.
Option B plays it safe with an orbiter, but adds an extra $70 million to NASA's most expensive planetary mission to date. At the end of the 60s, fighting the Vietnam War means America's debt is spiraling. An expensive mission to Mars is hardly a vote winner. Congress slashes NASA's budget, making the cheaper option A the obvious choice.
It was, in fact, quite surprising to many of the people involved in Viking that NASA chose option B over option A.
What's more, the agency requires engineers to build a second, identical spacecraft, Viking 2, as a backup.
And the rationale is that projects like Viking are rare. And when you do them, you should do them right.
To pay for it, NASA must spread the enormous cost over more years, delaying the launch to Mars from 1973 to 75. For mission designers like Gentry Lee, it's a godsend.
After we first started the Viking project, Jim Martin and all the rest of us knew that we had bitten off more than we could chew. But we didn't really want to go to Congress or to the president and say, I don't think we're going to get there by 1973.
Viking's complexity means every second will be needed to design and build the spacecraft. Searching for life on Mars will stretch those involved to the breaking point. Spring 1970. Engineers on Project Viking start the challenge of constructing America's first spacecraft to land on Mars. At the Smithsonian's National Air and Space Museum, it's possible to see the finished lander, designed to search for life on the red planet.
So as you can see, the lander is quite large. It weighs about half a ton, and it carries a pretty robust instrument package. It has a high-gain antenna for sending signals directly back to Earth. It also has 2 cameras that scan the landscape, and probably most importantly, a biological experimental package for analyzing soil samples.
If life exists on Mars, scientists expect it to be found in the soil. But that begs an all-important question.
How do you look for life on another planet when you have no idea what that life is like? You start with the assumption that at some basic level it's going to be similar to life on Earth.
On Earth, the simplest life forms are microscopic organisms. They're also the most abundant. Viking will search for similar microbes in Martian soil by looking for traces of gas produced as they live and breathe. To do this, the landers will carry 3 life-stimulating experiments. A lamp will warm Martian soil in the hope any organisms will react to light. Another adds varying mixtures of water and nutrients, encouraging microbes to exhale. The third adds drops of liquid nutrient, nicknamed chicken soup, coaxing any microbes to feed and metabolize. If Martian life exists, Viking will hopefully detect any gases the microbes produce, proving their existence in the soil. But engineering these experiments is a phenomenal challenge.
You're talking about a biological laboratory, something that would take up a significant amount of space in a scientist's lab. And you're shrinking it down to a box that's 1 foot on each side, a foot cube.
Restricted by size and weight, engineering Viking's biological experiments requires miniaturization on an unprecedented scale.
And the thing is jammed with, valves and pipes and miniature ovens and Geiger counters. It's diabolical to even think of trying to do that and doing it on a timetable.
1972, with 3 years till launch, keeping Viking on schedule is the job of Jim Martin.
Jim was an extraordinarily demanding project manager. Nothing short of excellence was good enough for Jim.
Jim runs a military-style operation, devising a notorious strategy to deal with the challenges.
And his concept was a top 10 problem list. And so top 10 problem list became very much a part of the culture of Viking. Sometimes the top 10 list had 11 items on it. And I mean, it was almost depressing as to how challenging some of these things were.
And the biology experiments were on that list for a very long time.
Incredibly, 40,000 parts are crammed into a space not much bigger than a briefcase.
I'm sure the engineers were tearing their hair out.
I'd say it almost brought us to our knees.
But the task is about to get harder still. Combating an invisible threat, biological contamination.
In order to prevent any terrestrial bacteria from going along on the trip, the lander had to be sterilized before it was put on the launch vehicle and sent to Mars.
Earth microbes can create a false reading and wreck the biological experiments. Worse still, they can contaminate Mars, irreversibly changing the planet. To sterilize the half-ton lander, Deputy Project Manager Gus Gustafaro turns to a profession that kills microbes for a living.
We looked at the medical practice, how they sterilize the equipment they have that might touch the human body. Why not use the same thing on electronic parts and materials that we're taking to the planet?
During construction, both spacecraft are repeatedly disinfected with antimicrobial fluids. But to be certain they're sterile, the team makes a radical decision to copy another hospital procedure.
And so we stole from them the idea of baking our whole spacecraft in a big oven.
Each lander is cocooned in a bioshell and placed in a 9-meter oven where nitrogen gas, heated to around 115 degrees Celsius, bakes them for almost 2 days.
I mean, you can imagine these engineers, okay? They've got to design things that have never been built before. And now somebody comes along and says, oh, by the way, everything you build has to withstand this baking in an oven of 240 degrees for 40 hours. And they must have just said, you gotta be kidding me.
Think about putting your camera or iPad in your oven and turning up the temperature and leaving it sit there for a few days. That's what we did with the lander. We couldn't think of any other way that guaranteed that we weren't taking any Earth life to Mars.
Over 5 years, every element of the spacecraft is designed and tested, hopefully ironing out each engineering pitfall. Now, with Viking built, it's time to put the engineering to the test. Summer 1975. Viking 1 and 2 will be launched on twin Titan rockets. The responsibility falls to Andy Stofan.
I launched rockets for NASA for 20 years. It's a strange job because it either blows up in your face or it's 100% successful. There's no in between.
Placing the spacecraft on a precise trajectory to Mars means both rockets must launch within a narrow time frame.
I was well aware of the importance of the Viking mission, so anything that went wrong with the vehicle would then lessen the probability of getting the 2 Vikings off.
August the 20th, Viking 1 gets away on time. But technical problems delay Viking 2 to the last possible launch day, September the 9th. Then something even the engineers can't control threatens to intervene.
The weather became marginal from a safety point of view as to worry getting struck by lightning either on the pad or during the launch.
Project manager Jim Martin consults local meteorologists and makes a call. Stop the countdown and wait for their predicted lull in the storm. With just hours of the launch window remaining, it's an incredible gamble. Thankfully, the weatherman's anticipated gap in the clouds passes right over the Cape.
3, 2, 1.
Viking 2 is launched with less than 5 minutes to spare.
To the great sigh of relief of myself and the Viking, the spacecraft people who were sitting there biting their nails.
The Vikings are on their way. Now the team must wait almost a year to get a shot at making history, attempting the first successful landing on Mars. June the 19th, 1976. A defining day for the engineers. Viking 1 arrives safely in Martian orbit. At over 300 million kilometers, sending communications takes around 20 minutes each way. So when the lander makes its rapid descent, it must be able to think for itself.
To do that was a whole new engineering challenge of creating an electronic brain that could carry out all of those things on board.
In the 1970s, computer code is typically stored on plastic tape. But sterilizing Viking at over 100 degrees Celsius creates a burning issue.
Had we heated the spacecraft that much, magnetic material would have melted away along with the tape in the storage system.
Engineers require a radical rethink. Viking sequencing expert Milton Holt thinks there's a solution.
And it looked like, hey, this is the way to go.
It's a metal storage device designed for the military. It's called pleated wire memory.
So on these strands of wire were the instructions that would get the lander to do everything it had to do.
It can withstand the sterilization, and it shouldn't be too difficult to manufacture, as we thought at that time.
In fact, engineers face a painstakingly intricate task.
It took 3,000 wires laid up by hand, and the intersection of each of these wires had to be totally in place within the width of less than a human hair.
This was like some kind of old world handcrafted creation, this very precise work. You could not afford to screw that up.
The finished computer contains all the information needed to land Viking on Mars, with a memory 100,000 times smaller than today's desktop computers.
This is going to sound unbelievable today, but that computer had 18,000 words of memory, and they sweated blood to get every one of them on there.
July 1976. Now in orbit, Viking 1 uses its cameras to give the team their first detailed view of its pre-selected landing site.
And the first pictures were alarming, and I really mean alarming.
The landing sites were chosen from pictures taken almost 5 years earlier, when the Mariner 9 spacecraft orbited Mars.
The Viking orbiter pictures were a factor of 10 better in resolution, and the change was just astonishing.
What appears smooth in the Mariner images now looks decidedly dangerous.
There were features that looked like giant fingernails had scraped across the surface.
There were huge boulders, trash bin-sized boulders, that could potentially kill the spacecraft if it landed there.
I mean, this was not the place that you wanted to throw a $500 million worth of lander at.
But luckily, the original decision to orbit Mars rather than head straight to the surface buys time to search for a safer site.
But they still had some time pressure on them. Viking 2 was on its way, and also the nation was watching.
As the new pictures would come in, the scientists would look at them closely and try to figure out, based on counting craters, how rough is the surface likely to be in that spot.
To say that that was an easy process would be a huge mistake, because it just took meeting after meeting after meeting.
First site, rejected. Second site, rejected. We rejected the fourth one, rejected the fifth one. It's now July the 10th or so, and the second Viking is about to get to Mars, and we can't manage two of them at once.
After 22 intense meetings, Gentry Lee and his exhausted team make the final decision.
3 o'clock in the morning, we're looking at the pictures of the sixth site, maybe it was the seventh, I forgot which one, and finally Hal Mazursky, who was one of the most eloquent spokespersons for exploration of the planets, put his head down on the table and said, "This is probably as good as we're going to find, and I'm tired." And so with that, we decided we would go down.
July the 20th, 1976. With the landing site chosen, it's time to make the descent. After final checks, the critical go command is sent. And Viking 1 is released from its orbiter.
Descent sequencing, we're at mission event.
I will never forget the moment that I first realized all the intelligence that we had or did not have had to be inside that computer, on board that lander, heading for Mars.
That separation, it's lost its mother, so to speak. It's by itself. It has to get there through a sequence of events that are pre-programmed.
For the next 3 hours, Viking is completely dependent on its onboard computer to safely reach the surface.
And there was almost a palpable sigh in the room, and almost as one, everyone looked at his or her watch and started mentally counting down 3 hours, so forth.
So apprehension, yeah, I think there's a lot of apprehension.
To successfully land, Viking's key components must each work perfectly, starting with the heat shield.
You're screaming in at thousands of miles an hour, and you hit this very thin atmosphere, but you hit it at very high speed. It's got to be able to withstand that intense heat of that deceleration.
Next, still traveling faster than the speed of sound, Viking must deploy a giant 16-meter parachute.
So for the first time, we've got a supersonic parachute, which is a whole design challenge in itself.
A challenge Paul Seamers wrestled with during Viking's development.
The first thing we did with the parachute to qualify it for Viking's flight was we put a model of it in the wind tunnel, and we had a big surprise. And that surprise was the parachute got torn to shreds. This turned out to be one of the worst days of my career, because I had to phone home to Langley and tell them I had just failed a parachute.
Paul's team discovers that at supersonic speeds, turbulent air behind the lander is too violent for the chute to survive. The failure means instant promotion onto Viking manager Jim Martin's infamous top 10 list.
We made the top of the top 10 problem list. How about that one?
Paul and the team must find a solution. They realize that by unfurling the parachute further from the lander, it experiences less destructive turbulence and remains in one piece. Now, back on Mars, the parachute works flawlessly, decelerating Viking to around 200 kilometers an hour. But a safe landing depends on overcoming one final challenge. Designing Viking 5 years earlier, engineers decide to use 3 retro rockets, slowing the lander to around 8 kilometers an hour at touchdown. But they discover a major flaw.
The tests were basically catastrophic. The propulsion system created so much disturbance, it would have compromised the science.
If there was any life there, the heating was such it would cook it, literally kill it. So we couldn't detect it if it was there.
For engineers, it's back to the drawing board. Instead of 3 large retro rockets with damaging exhaust, they replace them with a cluster of smaller ones, with exhaust plumes that won't cook the Martian surface.
It resembled a shower head. There were 18 nozzles on each engine, and that solved that problem.
Parachute separation.
But has it worked? Have the years of engineering toil finally placed Viking 1 safely on the surface of Mars? For everyone on the team, the moment of truth is about to arrive.
73 feet per second. ACS is close to vertical.
Come on.
Jim Martin and the team at the Jet Propulsion Laboratory count down the minutes to hear if Viking 1 has landed safely on Mars. Intern Andrew Chaikin witnesses the drama unfolding.
And, you know, we were waiting and waiting and waiting because those radio signals were still en route in that 20-minute delay from Mars to the Earth.
It's like waiting for the bride to come down the aisle.
ACS is green, 1.5 degrees per second max, 0.2 Gs.
Finally, after 20 agonizing minutes,
Touchdown, we have touchdown.
It was almost so fast that you couldn't take it all in.
We have a touchdown time of 12 hours, 12 minutes, 0.7 seconds.
And everyone started clapping, and a great sigh of relief. And it was just elation through the whole room.
7 years to the day after America lands men on the moon, engineers successfully place the first spacecraft on Mars.
My father, he was born in 1896, before the airplane and the automobile were invented. And he's here, excuse me for choking up, seeing his son enjoy landing a spacecraft on another planet. It was just remarkable. I would have given up all the money I ever made for that moment.
I think people just had to take a short time to breathe in and out that we had actually made it.
They were passing out champagne, and I had my first and only drink of champagne.
It's hard to state the feeling. I mean, it's a feeling of combined relief and excitement.
Job very well done. I'm assuming that we must be sitting right on the X. So everybody just did fabulous and couldn't be more pleased. Thank you.
But there's little time to celebrate, as everyone eagerly awaits Viking's first picture from the surface.
The anticipation of the first image coming back from Mars was extraordinary. I recall sitting glued to the screen in front of me.
With its unique cameras, it's hoped Viking will finally reveal Mars as never before.
It wasn't like a TV camera that would take the whole scene at once. It would take the scene line by line with a mirror that nodded up and down, and you would build up from left to right the entire scene.
And so we waited. And here's the picture in front of us. And on the left-hand side of the screen, down starts coming pixels.
And all of a sudden, 5 lines of picture came racing down from top to bottom. Just 5 lines, like that.
Information. Yep, that's it. That's it. Oh.
But then a few seconds later, another 5 lines.
Oh, more. You rocks. Oh. That's beautiful.
And then another 5 lines.
And by the time it got to the footpad, you could see the rivets. And I remember screaming, "Look at those bleeping rivets!"
Oh. Oh.
You could see them clearly.
It's incredible to see that Mars is really there.
You know, we're taking pictures on the surface of Mars. Nobody's ever done that before.
There was not a dry eye in the house. All of us just burst with joy because every single person on that team had lived in fear that what we were trying to do was beyond human capability.
The damn thing worked.
We were there, we did it, and now the science can begin.
With Viking 1 safely on Mars, what could be the most profound experiment in human history can start. The lander will gather soil to examine it for life, using its sampling arm.
At the end of the arm, there's a scoop. Once the arm has collected a sample, it can then be retracted and turned to deposit that sample into the biological experiment package.
The onboard computer commands the sample arm to unfurl. But with the engineers and the world's press eagerly waiting, there's a problem. The scoop fails to extend.
Oh my gosh, it was a panic time. After all the glory of landing safely would still not be a success if we couldn't get any material.
If we couldn't get a soil sample, that would mean that lander was out of business.
There was a lot of apprehension because we didn't know why at first it hadn't moved.
The engineers are dumbfounded. With the Viking 1 mission in jeopardy, everyone is scrambling to understand what's gone wrong.
And that was when this young engineer came in and he looked at me and he said, "I just went over the sequence. did you have a separate sequence to unlock the key? Oh, I said, and I remember that distinctly. I said, that's it, that's it.
The team can't quite believe it. A locking pin on the sampling arm's protective shroud has failed to drop free, and the arm is stuck.
Anytime we were testing on the Earth, we never had the locking key in, so we didn't have a sequence that removed the locking key first.
Incredibly, engineers have overlooked a vital part of the computer code that helps remove the pin. The solution is to write and then transmit the missing code to the lander. But with 1970s technology, that's easier said than done.
Well, the problem was the way you generated a computer program was you had a deck of cards and there were holes punched in these cards, and the position of the holes would tell you what command to load into the computer.
Working around the clock, the punch card code must be meticulously checked.
You'd be in there early morning, 2 or 3 o'clock in the morning, you'd put your deck in the computer, and it rejected. So then you got to go through this stack of cards and try to figure out, why did it reject this thing? Where did I make an error?
Milton and the team iron out every last glitch. Check the code works on Earth. And then it's radioed over 300 million kilometers to the lander. Now, they must wait.
The next day, when we got the pictures back, lo and behold, the pin was laying on the surface of Mars. And so we knew that this problem was behind us.
But Gentry Lee is not quite off the hook yet.
So I got to explain all this to the media. And of course, Jim said, now, don't embarrass yourself by saying you just forgot to unlock the thing. So I made up a perfectly honest story that made it sound much more complicated. I said, these instruments on Mars are very complex, and you have to study the sequences very carefully. And we found that we had made a slight error in the sequence. That was true.
We have touchdown.
Less than 2 weeks later, Viking 2 also makes it safely to the surface. Both landers sample Martian soil in their onboard labs. What they find remains one of the most contentious results in planetary exploration. The Viking cameras give scientists their first close-up look at the surface of Mars. But now all eyes are on the results of the biological experiments to see if they will detect microbes living in the soil.
There were 3 experiments. 2 of the experiments gave results that were not consistent with life.
That leaves one last experiment: adding nutrients to coax any Martian microbes to feed. What's detected comes as a shock.
The 3rd experiment, called the labeled release experiment, gave results that in 1976 indicated there was life on Mars.
But this positive result is controversial. On analyzing the soil further, Viking is unable to find any organic material, the stuff that life is made of, creating a dilemma. If there's life on Mars, where is the organic material?
One newspaper would say, Viking found life. Another one would say, Viking did not find life. And as a result, everybody was confused.
To confirm life, the science community requires more robust evidence, as planetary scientist Jim Green knows.
If each and every one of those instruments gave us a positive indication that a reaction could occur that was biological, that they were measuring, then we could be assured that it was life.
But Viking provides ambiguous results.
Now that means the scientific community couldn't get behind the idea that life exists on Mars today.
Even now, the Viking results are hotly debated, and the question remains, does life exist on Mars?
Well, we want to find that out.
Beginning in 1997, NASA returns to the Red Planet with a series of rovers. Studying the environment, their results have added to the speculation Mars might be able to support microbial life.
So now we want to go back and we want to attack it in a different way.
At the Jet Propulsion Laboratory, the latest generation of engineers, like Matthew Robinson, are designing a bold new mission with a twist.
We want to return the samples back to Earth so that we can process those samples with instruments that have much more precision and much more capability than what you can send to Mars.
NASA plans to bring back to Earth Martian soil and rock samples to analyze for evidence of both present and past life. Helping design the vehicle that's going to select the samples is Mars rover veteran Rob Manning.
Now we're building a new rover to land in 2020. However, it does something that no other rover has done before.
It has the capability of drilling rock, creating about a chalk-sized sample full of a history of Mars. This is an enormous engineering challenge.
Matthew and the team are experimenting how to extract a sample.
The way that we acquire samples is using a coring bit, much like a drill that you would get from a hardware store.
The drill will be able to extract core samples, from soft sandstone to the toughest granite.
Once we core into a rock, a robotic arm moves up and it goes over to the rover.
This core sample will then be very carefully put in a container that will then be left on the surface of Mars, along with many other core samples, which will later be collected by a future mission that will bring those cores back to Earth.
And that means a whole new generation of engineers are going to tackle this problem now. But they have one major advantage. They have the knowledge that has been given to them by the Viking engineers, demonstrating how we can do this.
It's a lasting testament to the Viking team that their technical achievements, made almost half a century ago, allow missions to land on Mars today.
It's amazing and mind-boggling that they were able to pull that off at such an early time in human engineering history.
It's like a symphony in many ways, and each of these individuals played their part.
All I could think of was, and I hugged the people around me, we did it! We did it!
We did the impossible. This is a symbol. This is my Mars 76 buckle. It was the biggest thing I've ever been involved with. And it worked, like I expected.
I have to confess, I've got a real feeling of pride of having been a part of it. And the emotional feeling's still there. That's everything I know, more than I know.